In this problem, we will go over how to calculate the delta H, the enthalpy of a reaction, utilizing the standard enthalpies of formations that are available in the back of the book. So this is problem 6.76. Let's follow along. Hydrazine N2H4 decomposes according to this following equation, where we have hydrazine, 3 moles of it breaking down to 4 moles of ammonia and 1 mole of N2 nitrogen gas. Continuing on, the problem asks us, given the standard enthalpy of formation is 50.42 kilojoules per mole, so that's something that is given to us. Calculate delta H, standard state, okay, that not or the O superscript means standard state, for its decomposition. Finally, part B is asking us that, telling us that hydrazine and ammonia burn in oxygen to produce H2O and nitrogen gas. Write a balanced equation of hydrazine burning in oxygen to produce water and N2 gas, as well as ammonia burning in oxygen to produce water and N2 gas, and calculate those standard enthalpies of standard enthalpy of the reaction based on the standard enthalpies of formation. So let's solve part A, and let's rewrite the reaction that we are supposed to calculate the enthalpy of the reaction. So let's solve part A here, recognizing that the enthalpy of the reaction is the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. Don't forget, we got to multiply by the coefficient. So not only is it the enthalpy of formation of the products, but we got to multiply by the coefficient. You know, call it M here, and I'll call the coefficients of each of the reactants. So let's look at Appendix 3 to get these values. So first of all, for NH3 gas, you can probably get this off of the internet or any other place, but here is Appendix 3, the standard enthalpy of formation of NH3. Okay, it's a gas. Make sure you have the right state. Gas, and then gas. So standard enthalpy of formation in kilojoules per mole is minus 46.3 kilojoules per mole. That's for 1 mole. Okay, this is important. That's for 1 mole. We actually have 4 moles here in the product, so it's going to be 4 times minus 46.3 kilojoules per mole plus the standard enthalpy of formation for nitrogen gas. So that's going to be 0. I know that because it's the baseline element. It's baseline, free alone standing, and natural abundance is a gas. It's 0. And I have 1 mole of it, so it's going to be plus 0 kilojoules per mole. All right, minus the sum of the enthalpies of formation of the reactants. We have one reactant, which is hydrazine, 3 times, because that's for 1 mole, 3 times, and the problem tells us it's actually 50.4 kilojoules per mole. That was actually given to us in the text of the problem. Okay, so that was in the problem. So doing this math, I'm getting 4 times minus 46.3 is minus 185.2 kilojoules per mole. Okay, plus 0 is 0. Okay, plus 0 minus 3 times this number here, so it's minus 151.2 kilojoules per mole. And minus 185.2 plus a minus 151.2 gives us the minus sign, minus 336.4 kilojoules per mole. The minus sign tells us this is unequivocally an exothermic reaction, so that this reaction is releasing heat, and the heat is on the product side of the equation. It is liberated. It gives off heat. Hydrazine and ammonia burn in oxygen to produce this product and this product. Write their balanced equations and do the exact same thing that we did in part A. Okay, hydrazine burning in oxygen, they tell us it's water and nitrogen gas that was given to us in the problem. So what we need to do is write out the formulas and balance the equation. All right, here's the equation of hydrazine burning in oxygen. They tell us it's water and nitrogen gas. And let's balance this. I have 4 hydrogens. So to get 4 hydrogens, I'll put a 2 here for 2 waters. So 4 hydrogens, 2 N's, 2 N's, 2 O's, and then I have 2 O's. So that is hydrazine burning in oxygen. So that's our first one. And let's go ahead and calculate the enthalpy of formation. Again, sum of the products minus sum of the reactants. So sum of the products minus sum of the reactants, they are enthalpies of formation. So I got 2 moles, so H2O liquid, not H2O gas. So H2O liquid is minus 285.8 kilojoules per mole. Don't forget we got to multiply it by 2. All right, nitrogen we found was 0 kilojoules per mole. It's standard base element. Minus O2 is also going to be 0. That's your standard baseline element. So you can look it up in the back of the book, but I already know it's going to be 0, so I'll save some time. And then hydrazine, they tell us, is in the problem 50.4 kilojoules per mole. So doing this math, 2 times minus 285.8 is nothing more, 2 times minus 285.8 plus 0 minus a 0 minus 50.4. So 2 times 285.8. Okay, we're going to distribute that minus. So minus 50.4 kilojoules per mole. And doing that on my calculator, I'm getting an answer of minus 336.2 kilojoules per mole. Right, so that's hydrazine burning in oxygen. Let's do the same thing. The problem is asking us for NH3 ammonia burning in oxygen. It will give us the same products. All right, so now we got hydrazine burning in oxygen. Now we'll do ammonia burning in oxygen. We have to balance this equation here. So we have here 2 nitrogens to 1 nitrogen. So I'm going to put a 2 here. That changes this hydrogens to 6. So I'm going to put a 3 here to get those hydrogens to 6. And now I have 3 oxygens here, but I only got 2 oxygens there. So I'm going to use the fraction 3/2. When I use the fraction 3/2, 3/2 times 2 gives me 3. We don't usually like to have fractions in as our coefficients. So I'm going to multiply both sides of the equation, reactants and products, by 2. So doing that, this will give me 4 NH3 gas plus 3 O2 gas goes to 6 waters, 6 H2O liquid, and then 2 times N2 gas. All right, now we'll do our products over reactants, getting our enthalpies of formation from the back of the book. So don't forget, for water as a product, it's going to be 6 times what we found for water in the back of the book for the standard enthalpy of formation. And just a reminder, that value is, looking at the back of the book, just as a reminder, that value is minus 285.8. That's for 1 mole. We got to multiply it by 6 because we got 6 of these guys. So it's going to be 6 times minus 285.8 kilojoules per mole. Okay, plus 2 times the enthalpy of formation of nitrogen gas, which is actually 0. Minus, we put our big brackets here, 3 times the standard enthalpy of formation of oxygen, which is a 0. That's the base element. You can look it up. You'll see 0 there to save some time. I won't do that. And NH3 gas, the standard enthalpy of formation for NH3 gas. Looking that up, okay, make sure you look it up for NH3 gas. And NH3 gas is going to be minus 46.3. Okay, we got 4 of these, so it's going to be 4 times 46.3 kilojoules per mole. Actually, 4 times minus 46.3 kilojoules per mole. All right, doing this math, we have 6 times minus 285.8, which in my calculator computes out to minus 1714.8 kilojoules per mole, plus 0 minus 4 times a negative 46.3. So let's be careful in our math here. This can definitely trip people up. Minus 4 times a negative 46.3 is minus 185.2 kilojoules per mole. And I'm left with minus 1714.8 minus a minus 185.2. Minus a minus becomes plus. So getting an answer of minus 1530 or so, rounding, kilojoules per mole. Okay. So both are exothermic reactions. One is minus 1530 per mole of NH3, and the other one is minus 336.2 kilojoules per mole of hydrazine. Both are exothermic. Now, continuing on with the problem, they ask us to compute on a mass basis per kilogram, which is a better fuel. Okay, both give off heat, so both are good fuels. In terms of the magnitude of heat per kilogram, which is the better fuel? So this is per mole of hydrazine. So let's go ahead and convert that to kilograms per kilograms of hydrazine. And this is per mole of ammonia. Let's go ahead and figure that out per kilogram of ammonia. Okay, this is what we calculated. The enthalpy of that reaction burning in oxygen. 1 mole of hydrazine contains about 32.06 grams of hydrazine, okay, based on the periodic table atomic weights. Okay, the moles cancel. Let's go ahead and convert these grams to kilograms. So for every 1,000 grams, there's 1 kilogram. So the grams and grams cancel. And so per kilogram of hydrazine, there's about minus 10,486 kilojoules of energy released because of that negative sign. Kilograms of hydrazine, which is N2H4. Ammonia, if you remember, we calculated about minus 1530 kilojoules per mole of NH3. We know that for every 1 mole of NH3, based on the atomic weights in the periodic table, there's 17.04 grams of NH3. Okay, let's use the kilogram to gram conversion factor. It's 1,000 grams in 1 kilogram. And like before, the moles of NH3 cancels with the moles, the grams cancels with the grams. And doing that on our calculator, I'm getting minus 89,789 kilojoules per kilogram of NH3. So which is the better fuel source? Which burns more energy per kilogram? And you can see here, per kilogram of hydrazine, we burn minus 10,500 or so kilojoules. For every kilogram of NH3 ammonia, we burn about minus 90,000 or so kilojoules. So this is the better fuel source. More negative, more energy released. And per kilogram, NH3 is the better fuel.